You have probably seen the new wave of AI PCs, Intel and Ryzen laptops promising on-device AI right out of the box. But here's the problem. Most of them choke the moment you try to run a real large language model. Meanwhile, a single NVIDIA desktop card can casually handle models that bring those laptops to their knees. So what edge does NVIDIA actually have? And why is VRAM the real engine of local AI? Stick around. By the end of this video, you will know exactly why your shiny AI laptop might be more marketing than machine learning. Let's answer the core question first. Why do large language models care so much about VRAM? An LLM is essentially billions of numbers, model weights, that must be loaded into memory before the model can respond to a single word. Every time you type a prompt, the GPU performs massive matrix multiplications across all those weights. Billions of them, repeatedly and in parallel. If those weights don't fit inside VRAM, the GPU has to constantly pull data across the PCI bus or reach back into system RAM, and that latency kills your speed. So the very first hard limit for running LLMs locally is not your CPU speed, it's how much VRAM do you actually have. Here's a mental model that makes this click. Picture VRAM as a giant whiteboard right beside you. System RAM is a second whiteboard in the hallway. If your entire problem fits on the whiteboard next to you, you work fast. But if you constantly have to jog down the hallway to copy pieces back, every single step slows you down, even if you're brilliant. That's VRAM versus RAM for AI, in a nutshell.
So what makes VRAM special? VRAM is dedicated high-bandwidth memory soldered directly onto the GPU, purpose-built for moving enormous tensors and image data at very high speeds. It has two defining properties. It is physically close to the GPU cores, giving it very low latency, and it offers far higher bandwidth than anything a CPU can access. Integrated graphics on Intel or AMD chips do not have dedicated VRAM. They carve a chunk out of your regular system RAM and use that as GPU memory. That means your integrated GPU is competing with your CPU, your operating system, and every open application for the same pool of slower memory. Fine for spreadsheets and YouTube, painful for multi-billion parameter AI models. So when you see AI PC up to 32 gigabytes RAM, let's be clear, that is not 32 gigabytes of VRAM for your LLM. Your integrated GPU might only be allocated a few gigabytes, and even that runs at a fraction of the bandwidth of real VRAM on a discrete NVIDIA card. Now let's look at what NVIDIA is quietly doing while the AI PC marketing machine runs hot. For local AI, NVIDIA cards break down into three practical tiers. Entry tier, cards like the RTX 4060 and 4060 Ti with 8 to 16 gigabytes of VRAM. Good for small 7 billion parameter models at lower quantization, basic stable diffusion, and SDXL with some compromises. Sweet spot tier, the RTX 4070, 4070 Super, and 4070 Ti Super with 12 to 16 gigabytes of VRAM. Comfortable for 7 to 13 billion parameter LLMs, SDXL with ControlNet, and solid context windows. This is where most serious local AI builders land. Heavy tier, the RTX 4080, 4080 Super, and 4090, running 16 to 24 gigabytes of VRAM. This opens the door to 13 to 34 billion parameter models, larger batch sizes, multimodal workflows, and high-resolution generation. And on the horizon, next-gen RTX 50 series cards are pushing VRAM and bandwidth even higher, with new low-precision formats like FP8 and FP4 that let you squeeze bigger models into the same memory footprint. The rule is consistent. More VRAM means bigger models, longer contexts, and faster throughput.
Here's a question that sounds reasonable on the surface. If modern laptop CPUs are getting faster with NPUs and improved integrated graphics, should not they be good enough? This is the part almost no tech review explains clearly. The bottleneck is not just compute power, it is memory architecture. An integrated GPU is fundamentally constrained by shared system RAM, limited bandwidth, limited capacity, and constant competition from everything else running on your machine. Yes, you might technically run a tiny quantized LLM on an AI PC, but it will be slow, context-limited, and frustrating for anything beyond a lightweight chatbot. That's why the moment someone tries a real local AI workload, they stop asking which CPU and start asking which NVIDIA card and how much VRAM. To be fair, none of these chips are useless. CPUs, NPUs, and integrated graphics all have their place. They shine for on-device transcription and voice recognition, lightweight recommendation engines, small assistant models under 1 billion parameters, and background AI features like noise cancellation, photo enhancement, and smart autocomplete in Office apps. But LLMs like Llama 3, Mistral, Qwen, or any fine-tuned 13 billion-plus model? Completely different ballgame. These models were built around massive parallelism and enormous parameter sets that need wide memory buses, deep VRAM pools, and thousands of specialized compute cores working simultaneously. Discrete NVIDIA GPUs bring 3 things no integrated chip can match. First, enough VRAM to hold the full model weights alongside a large context window. Second, the raw memory bandwidth to feed those weights into thousands of CUDA and tensor cores without starving them. And third, a mature, battle-tested software stack, CUDA, CUDNN, TensorRT LLM, PyTorch, an ecosystem thousands of developers have spent a decade optimizing specifically for these chips. Edge AI tasks? Sure, a laptop NPU can handle those. But run Llama 3 70 billion at useful speeds? That's a discrete GPU job.
Let us bring this to life with a concrete example. Setup A, a thin and light AI laptop, 32 gigabytes of RAM, integrated graphics. Setup B, a mid-range desktop with an RTX 4070, 12 gigabytes of dedicated VRAM. On the laptop, you load a 7 billion parameter model at aggressive quantization. Context window is tiny. Token output is sluggish. The system is constantly shuttling data between CPU and iGPU. It works, barely. On the desktop, that same 7 billion parameter model loads entirely into VRAM with headroom to spare. Context window is open. Responses are fast. And with the memory left over, you can run image generation or a second pipeline in parallel. Same marketing buzzword, AI ready. Completely different reality. The gap is not about the CPU brand or clock speed. It is about the memory architecture sitting behind the silicon. So next time you see AI PC plastered on a spec sheet, ask the right question. How much dedicated VRAM do I actually get, and on which GPU? NVIDIA's real advantage over integrated graphics is not just raw compute. It is the full stack, memory capacity, bandwidth, architecture, and years of software ecosystem built around running serious models. If you're chasing real LLMs, big context windows, or anything beyond a light chatbot, you're not shopping for a brand name, you're shopping for VRAM. If this video helped you cut through the marketing, hit like and subscribe.